Good morning. What I'd like to do today is describe for you in visual terms the basic elements that are used in structural analysis. And the purpose of this is to get you a sense of how these work from an intuitive point of view, so that when you get to statics and mechanics next, you'll be able to look at these things from a mathematical point of view, and they're going to make some sense. These are diagrams that you'll be developing in statics and mechanics. These are derived from mathematical equations. And you can see that these curves are the result of forces that are generated by the configuration of the structure, where it's got a support point here and a support point here and so on. That's all defined by mathematical equations and then plotted out accordingly. This one, for example, looks an awful like a bridge. The purpose of my discussion here is so that when you calculate these things mathematically, they're going to make some sense to you. There's two elements that we look at in structure. There's tension and compression. Tension is pulling, and you can think of materials that support pulling, wire, rope, and so on. And those elements, by and large, don't work very well when you push on them. You can't push a rope. Compressive elements are elements that are being pushed on. And you can think of a column, a table leg, a post. Materials that are good in compression, like concrete, you can push on concrete a long time before it crumbles. It's very good from that point of view. But coincidentally, concrete has very poor properties in tension. And so what we do is we mix concrete and steel together so that we put concrete rods in the right places resisting the tensile stresses on the concrete, and then the concrete acts as the compressive element, and as a result you have a system that does both. Materials that are good in both, steel, wood, fiberglass, that's the resin that's good in compression, it's the fiberglass that's good in tension. So here's two guys holding a rope, and suppose it's a pretty heavy rope, so they'd feel it, and the shape of this rope forms a curve. And in statics and mechanics, you'll calculate the shape of that curve based on its span and load and so on. But just remember that it forms a curve. That curve is called a catenary, and it's a natural shape of a tensile member essentially being draped. These two guys are going to take the weights of that rope, if it's a heavy rope, and carry it to the ground. So they're acting as compressive elements. Now, if it's a very heavy rope, they may be pulling on it a little bit as well as bearing it on their knees, and I'll show you how that works in a moment. So here's a situation. You can think of this as kind of a valley. These are replacing the guys. There are a couple of concrete columns. This is a heavy cable. Say if this is 500 feet, this might be 6 feet wide or in diameter. These are compressive elements. This is a catenary in tension. Now suppose you add a load to it, say cars, trucks, buses, that you might find on a bridge. And what you could do then is you could just simply take that load and attach it directly to this. It's a uniform load, and so you uniformly add it to this cable. These loads will increase by the amount that you've added, but effectively the relationship is the same. It's just grown more. Well, then think of lowering that load of cars, trucks, and buses, and you can lower it on tensile members to just simply move it down. And what happens then is that the result is essentially the same. All of this load is going down to the ground on these compressive members just as it did before. Now think of taking that curved load and flattening it, which starts to look an awful lot like a road deck. All you've done really is added some tensile members that are longer, and effectively you've got a straight line. Now the thing that I was mentioning about those guys pulling back, well, that's what's happening here. Is this is a compressive load going down. This tensile load is at an angle, and the way that these things work is that this is a steep angle. This will be down about to the bottom of that angle of that force, and then you form a rectangle, and then there's a horizontal component that closes the box. And so if this was very shallow, this arrow would be much longer, this would be shorter, meaning there's a really strong pull in this column. In this case, there's a pull in the column, a pull in the column that we have to resist. And the way we do that is you take this piece, half the bridge, flip it over, and what you've done then is balanced these angled tensile pieces so that there's no tendency for that column to move back and forth, and all of the load then is going to the ground. Then, if you think of taking that array that I had and then just doubling it, it's starting to look an awful lot like a bridge. And all one would have to do then is take little decking pieces to connect it, which would involve beams and slabs, which I'll talk about tomorrow, and you have, in fact, what looks very much like a suspension bridge. And there you have it. The Brooklyn Bridge in New York, compressive members, catenary, and then tensile members carrying this bridge deck across, and then balancing it so that the columns that are supporting it are stable.